I'm going to repeat myself for the sake of the recording. If you see a natural log as in an integrand, first try u substitution. Let u be that entire logarithm or that entire inverse trig function and see if a u substitution works. If it doesn't work, then your function is still going to be a u, but now it's a u and a dv multiplied together, and integration by parts is done. So here we go. My u needs to be the natural log, and everything inside of it has to go there with it. dv is everything else. The dx always goes with the dv, though. Now, the u gets differentiated. When I differentiate, I'm looking at the natural log of bleh, and I chain rule. The derivative of natural log of bleh is 1 over bleh. Shove the baby in, multiply by the derivative of the baby, and you have differentiated, but don't forget to multiply by the differential dx. And then I need to integrate the integral of dv is v, the integral of dx is x. We don't need a plus c in this situation because it will be absorbed into the bigger unknown constant at the end of the entire integration. So now the question is, do you remember the formula for integration by parts? And it's u times v minus the integral of, and you multiply your two results, the result of taking derivative and the result of taking an integral, otherwise known as voodoo, ultraviolet voodoo. At this point now I'm going to multiply the v in front of the u. And then I'm going to multiply this x with all of this. I'm going to go ahead and distribute it through and write the denominator correctly. So x times 2x minus 1 . So I'm done with part of it, and now I need to look at the integral at hand. Notice it's a polynomial over polynomial. So what is the first question? The first question is that numerator less degree than the denominator? And the answer is no. That means it's time for some division fun. I am dividing by x squared minus x plus 2. My dividend begins with 2x squared. And then I have to determine x squared times 2 gives me the 2x squared. And then I need to multiply it all the way through. And once the quotient has its constant term, then anything that does not make up the dividend in the interior of the boxes being added together before this line, everything else is remainder. So I again look at that numerator. I've got 2x squared. I need minus x. Right now I have minus 2x, so I need to add x. And then I need to not have anything else, and I have a plus 4, so I need to subtract 4. I end up with subtracting the integral of the entire giant polynomial quotient 2 plus remainder x minus 4 over my x squared minus x plus 2. I'm ready to integrate the 2. Then I look at the polynomial over polynomial. It's now less degree than the denominator. Can I factor the denominator? And remember that if you want to determine whether you can factor a quadratic, the quadratic formula has b squared minus 4ac under the square root. My b is -1, -1 squared is 1, my a is 1, my c is 2. This is a negative number. A negative number under a square root says I'm not real. Although it is real, it's just not a real number. Anyway, that means, guess what? There is no fraction decomposition. So what's next? I can do trig substitution. I'm going to have to do trig substitution. But I want to see if I can lessen the amount of trig substitution by seeing what can I use as just u substitution. Because u substitution will hands down be easier than whatever you have to do to get that piece through trig substitution. I'm going to erase the division over here. If I do a u substitution, then my u is x squared minus x plus 2. My derivative is 2x minus 1. And I want to make sure that this entire x is part of the du. And I need to figure out how much of the constant do I need to bring in so that I can separate the numerator. Because this is just an x, I need to factor a 2 out right here, leaving me with x minus, oh yay, fraction 1/2. So now what I know is that I want to split up x minus 4 into x minus 1/2, and then what's left over, subtracting 3.5 or 7/2, and that's how I'm going to split it up. Now, before I forget that I have a bunch of other stuff, I'm going to write some of this down. I started off with x times natural log of stuff. And then I have minus the integral of 2, which is going to be 2x. And then I have minus splitting this numerator. And I want to make sure to distribute that subtraction. So I have the x minus 1/2 piece of the numerator. And then I have minus negative 7/2 times the integral of just 1 over that denominator. And here we are. Let's integrate the u substitution. And if we recall, that was so x minus 1/2 times dx is replaced with a 1/2 du. And then I have a 1 over u from there. So minus 1/2 natural log of the absolute value of u, but I don't need absolute values because u is a quadratic that will only be positive. And then over here I've got a plus 7/2, and I'm going to write this down here just to be ready to say the answer. And now it's time for trig substitution. But wait, I don't have a sum or difference of squares. Oh no, what does that mean I have to do? Complete the square. So I have x squared minus x and a plus 2. I need to add a number and compensate by subtracting that same number so that this will factor into a binomial square. Then I go through the work of the middle term is negative 1, divide by 2, and square that number. And I've already factored, and now I just need to do 2 minus 1/4. That's going to give me 7/4, and I'm adding it. And so now I'm focused on this integral right here. And that integral is dx over x minus 1/2 quantity squared plus 7/4. Okay, now I see a sum of two squares. I'm going to use which trig function? I'm going to use tangent. And I'm going to set tangent equal to the function that is being squared, x minus 1/2, divided by the number that is being squared, the lovely square root of 7 divided by 2. I'm going to make a triangle. And I'm going to find the derivative. The derivative of tangent is secant squared theta d theta. And then actually this would be easier if I right now multiply the root 7 over 2 over here to the left side so that I can more easily just drop that constant, and then the derivative on the right is just 1 times dx. Now because tangent is opposite over adjacent, I've got my opposite side over my adjacent side. And Pythagorean theorem is going to take leg squared plus leg squared and square root it after adding that together. But I happen to know that the sum of those squares is just that quadratic that I started with. And quite honestly, I'm a bit tired of having to rewrite this darn thing. So, and by what quadratic is that, I mean all the way back over to here. This is this mess of the sum of the two squares. So I would rather, honestly, just write that. And, you know, I could also keep in mind that actually that's all this denominator is if I want. I don't have to. But basically, this is the square of this side, regardless of how I write it. I'm prepped with substituting in dx. And then I can look at the side that has that x squared minus x plus 2 is the hypotenuse. The side that has just a constant is the adjacent. So cosine's reciprocal is secant. And secant is that hypotenuse over the lovely root 7 over 2. Now I'm going to multiply that root 7 over 2, and then I'm going to square both sides. And now I can say that this denominator is equal to all of that. And now my integral is the square root of 7 over 2 times secant squared theta d theta divided by, and if I square this number, that will be 7 over 4 times secant squared theta, cancellation, and then with the numbers, actually it might have been easier if I had left it as just root 7 over 2 quantity squared, because then I can see that I cancel one of them. And in the denominator, I can flip that to the numerator to be 2 divided by root 7. And that is my integrand. So when I integrate that with respect to theta, I get that constant times theta. Theta is the inverse tangent. So I have isn't it just lovely? Yay! Who had fun? Yeah! All right, now I'm going to stop the recording, and I officially have both problems